Hi, welcome to the bonus part of my talk on the composition complexity of majority. I just wanted to say a few words about the proof of the main lemma for general Q, because I think it's kind of cute. So if you I'm going to assume that you've watched the main part of the talk, or that you've maybe read the introduction of the paper or something like that. So I'm going to go straight into it. Okay, so we have this lemma. The idea is that we assume that we have some kind of circuit that computes the Hamming weight of its input bits, and it has a structure. So there's a bunch of sub-functions, g1 through gm, and then there's a combining function h. And here we're only going to, the lemma goes like this. It only assumes that for some variable xi, it is created a few times by the sub-functions, and it deduces from that that the subfunctions must say a lot about that variable xi, where say a lot means is in terms of mutual information, and the mutual information between xi and the output of the subfunction has to be something that is non-zero and is exponentially decreasing in Q, the number of times that xi is queried. Okay, so how did we go about it for the baby version of the lemma where Q equals 1? There we actually proved that the mutual information was equal to 1, or equivalently that if you knew all of the subfunctions g1 through gm, you could deduce xi exactly with 100% certainty. Here it's not going to be possible to do this in a general case, so instead we're going to have to argue that you can say something non-trivial about xi. So maybe you can give a better than 50-50 chance, you can make a guess that is better than 50-50 chance about xi, at least in some cases. Concretely, an equivalent way to phrase this lemma is to say that instead of looking at mutual information, we're going to look at the entropy. So we're going to look at the remaining entropy of xi once we know g1 through gm. So we're going to look at this quantity, xi given g1 through gm. And this is a quantity that we're going to upper bound this quantity by 1 minus 2 to the O of q. So if we knew nothing about xi from g1 through gm, the remaining entropy would be 1, because xi is just a random bit. So here we're saying that we can kind of do a better than random chance guess at xi once we have g1 through gm, and how much better than random chance is quantified by this expression, 2 to the minus O of q. Okay. But yeah, let's get into it. The setup of the proof is very similar in spirit to the proof of the baby version of the lemma with q equals 1. The first step is to ask this kind of weird question of what if we only knew the result of the subfunctions that do not query xi. So to kind of formalize that, or at least hand wave in a slightly clearer way, we're gonna split the hypercube 0, 1 to the n into subsets depending on the value of g2 through gm. So maybe we're going to focus on some subset S, which fixes the values of g, j of x for all j not querying xi. Sorry. Okay. And once we look at that, so first of all, it's kind of fine to focus on such a subset because we're conditioning here on the results of the subfunctions g1 through gm. So it's fine to focus on a subset where some of those values are fixed. And actually, we're going to prove that this remaining entropy of xi is smaller than 1 minus 2 to the minus of q in each of those sets S. So we're going to just like take some S and show that within S, the remaining entropy is small in that sense. Okay, so once we fix the values of some functions that do not query xi, sorry, let me write that completely. We're going to look at the set W, which is going to be very similar to, like, exactly the same as we defined in the proof for q equals 1. So W is just going to be the possible Hamming weight values for x's in this set. So just to write in math, this is what W is. Like, if you only knew the results of the functions that do not query xi, what are the possible values of the Hamming weight of x? And in the proof with q equals 1, we observed that there's only 2 possible values because we knew all but one of the subfunctions. We knew all but the one subfunction that did query xi. And since, like, in this diagram, we if we know all the values g1 through gm, then we can plug them into h and get the value of the Hamming weight. So the only remaining uncertainty was the value of the subfunction that queries xi. And here, similarly, if we know all the subfunctions except for those that query xi, then the only remaining uncertainty is the k values of the subfunctions that do query xi, and all of those are bits by assumption of the model, and so that's only 2 to the k, 2 to the q values. So all this to say that the size of W is at most 2 to the q. So okay, so we have fixed the subfunctions that do not query xi, and now looking at the possible values of the Hamming weight given this, we only have 2 to the q many of those. Okay, so that's the first step. It's exactly the same as the proof for q equals 1. In the proof for q equals 1, we then study the properties of this set, and then we kind of realized that if we knew this set and if we knew the Hamming weight of x, then just by looking at whether the Hamming weight of x is the first or the second element of that set, we could discover the value of xi exactly. Here, that's where the arguments kind of diverge. Like, that's where this argument has to be a bit more subtle, a bit more complicated. And the way it goes is I'm going to show you a pretty elaborate graph, which is going to plot 2 probabilities. So we're still focusing on this subset S, and I'm going to plot some probabilities conditioned on x being in S. So the x-axis is going to be the Hamming weight, and yeah, maybe let me denote a W actually. Yeah, let me denote a W, and I'm going to plot 2 different probabilities. The first one is going to be the probability that xi equals 0 and the Hamming weight is equal to W given that x is in S. So it's over this set S. If you draw a random string within that set, what is the probability that the Hamming weight is at W and that xi is equal to 0? And I'm gonna draw a second. I'm gonna graph a second probability, the same thing but with xi equals 1. Okay, so yeah, this is going to be a graph with like, let's say between like 0 and n. And we're going to get like a bunch of blue and red points. And I'm going to now argue about how this graph should roughly look like. Okay, so maybe I just draw a bunch of points and then explain what I'm doing here. So, okay, so I'm going to start with a point over here, and then maybe it's going to be 0 for a while, because like only like 2 to the q of those red points and of those blue points should be non-zero, because we had only 2 to the q possible values of the Hamming weight given that we were in x. sorry, that weighted in S. Okay, so yeah, let's just draw a bunch of values. Boom. And maybe at some point we get some non-zero probability values. And clearly it kind of looks like a staircase by that point. Something like this. Okay, maybe it keeps increasing, like to some peak, but then it decreases, something like this. Okay, something like this, and then maybe that's the end. Maybe that's all that it was. Okay, so yeah, why am I drawing it in this way? Okay, so you might notice that whenever I drew a red point and the blue point on the next W, like the next value of W, they had the same height. So and those like lines are all horizontal. Why is this the case? I think that this has to be the case because if you look at the x's that have having weight x and xi equals 0, they're an exact, there's an exact pairing with the x's that have having weight equals w plus 1 and xi equals 1, because those are like if one of them is in, like, okay, so like if you have an x in that left red set, then if you flip its value of xi, then you should get to the right blue set, because we defined S crucially based on only the subfunctions that do not query xi. So that means that some value x is in S if and only if x XOR I, which denotes the x with its I coordinate flipped, is also in S. Okay, so that justifies why I'm drawing the red point at the same height as the next blue point. Okay, that's the first observation. The second observation is that whichever set of values we have with non-zero probability weight, there's at most 2 to the q of them, because the set of values with non-zero probability is exactly the set W that we defined, and we showed that the W had size at most 2 to the q. And now that I'm here, I'm drawing it as kind of like a contiguous segment, but the argument is not actually going to depend on that. It's just simple to draw like a contiguous segment of non-zero probabilities. Okay, so those were like the first 2 observations. Now here's the kicker. Probabilities sum to 1. So in particular, the red points have to sum to 1, and the blue points have to sum. This is not quite true. Sorry, that like the sum of the red points and the blue points has to be 1, because we're covering all possible values of the Hamming weight and all possible values of xi. So, so yeah, like the sum of of all those points has to it has to sum to 1, and there's only like 2 to the q, maybe times 2 of those points, because there's only 2 to the q possible values of the Hamming weight where you can get a non-zero value, and there's only like a blue point and a red point that you can have at each of those. So all in all, it says that the highest point, okay, it's like you have a bunch of things that sum to 1, and there's only like 2 times 2 to the q of them. So like the peak has to be at least 1 over 2 times 2 to the q, and like we're just going to simplify it as like 2 to the minus of q. Because you get a peak of 2 to the minus of q. And importantly, you start from 0, because the first blue point has to be 0, because there's no way you can have Hamming weight 0 and yet have xi equals to 1. Okay, so that's, you start from 0, you have a peak at, like, that's pretty high, like 2 to the minus of q, and you also have like only 2 to the minus of q, 2 to the q non-zero values. So that means that, maybe let's erase this, that there must be some coordinate where there's a big jump, where there's a big jump up. So there's must be like some coordinate where the red point is quite a bit higher than the blue point, and I have quite a bit higher. I just mean like 2 to the minus O of q again, because like you have to get 2 to the O of q, sorry, 2 to the minus O of q, and there's only 2 to the q steps, so there's at least one step, which is like maybe 2 to like minus 2q or something like that. Okay, so in math, what I'm saying is that there's just some like special Hamming weight value w star in among the possible Hamming weights, so that the red point is much higher than the blue point. So that means that the probability that you get xi equals 0 is much higher than the probability that you get xi equals 1. Let me write that down. Again, condition on x being in S. Right, it's bigger than 2 to the minus O of q. And I claim that now we're basically done. So you have some possible value of the Hamming weight w prime, for which there's a big difference between the probability of xi being equal to 0 and the probability of xi being equal to 1. So that means that at least for that coordinate, you can do a better than 50-50% chance, like 50-50 random chance of guessing xi. Like for this specific w prime, do better than random chance at guessing the value of xi. And this specific w star is also fairly likely, because since the red point is quite a bit higher than the blue point, then like sum of the two has to be like significant. You're at least 2 to the minus of q fraction of the time, condition on x being in S, you're going to end up in this Hamming weight w star. So that means that at least a significant fraction of the time, you have a significantly better than random chance guess at xi. And that is sufficient to show that the remaining entropy, once you know, okay, what do you need to know here? You need to know S, and you also need to know the Hamming weight, because you need to know whether you're in W prime. So as long as you know the Hamming weight and you know S, and knowing S means just knowing the values of Gj of X for Gj not occurring Xi. So as long as you have that, you can get like 2 to the minus of q better than random chance guess. So that means that the entropy is at least 1 minus 2 to the minus of q. And we're almost done. The last step is just to observe that if we actually do know this, because the actual entropy that we had to lower bound was this entropy, where you know everything about this result of the functions. And this is like a stronger conditioning, because clearly if you know all of these, and you know all of the ones that do not carry xi, and also since you know all the results of the subfunctions, you can plug them into H and figure out the Hamming weight. So that means that the entropy here is at most the entropy that we just bounded. Sorry, this is in the wrong direction. It should be less than 1 minus to the minus of q. So now we have this entropy is less than 1 minus 2 to the minus of q, and that is exactly what we needed to prove. So just to recap, the idea is you condition on the subfunctions that do not query the value xi. Then you realize that this leaves only a small number of possibilities for the Hamming weight. And because of that, there must be some specific Hamming weight, w star, for which there is a big discrepancy between the probability of getting xi equals 1 and xi equals 0. And from that, you get a gain in entropy, and that shows that there's a significant amount of shared information between xi and the result of the subfunctions. That's all for this video. Thank you for watching.